Today we are going to be solving logarithmic equations. Make sure that you have your notebook available to copy these notes into, setting up your table of contents, because don't forget at the end of the semester we do have a notebook check. If you want to shorten it to solving log equations, that is just fine. But the first topic or first vocab word we're going to talk about today is the word exponentiate. We're just going to talk about that because I use it in some of the steps. And it's not a big deal. We've already actually done it before. To exponentiate is to change from log form to exponential form. Step one, when we are solving equations, is we want to get the log alone. That word was left out. We want to get it alone on one side of the equal sign. Okay. Alone means the log is going to have a base and an object, and that's it. It's not being multiplied by a coefficient. It's not being added or subtracted. If it is, then we need to get rid of those things. Right? So first step is to get the log alone on one side of the equal sign. Second step is to exponentiate. Okay, so we're going to exponentiate by changing it to exponential form. And when we do that, then we will no longer have the log. Right, so using the base that's there, rewrite it in exponent form. Last step is once we've gotten rid of the log, we're going to get x by itself. So whatever form x is in, we may need to use our opposite operations to get it by itself. Once we get x by itself, we are done. All right, and we also want to make sure that we check for extraneous solutions. We dealt with extraneous solutions with rational functions and also with radical functions back in Unit 4. So for log functions, it looks a little different. We just want to make sure that when we find a solution or an answer, if we plug it back into the object, we want to make sure that it doesn't create an object that is either negative or zero. Okay? We cannot take the log of something that is negative, and we cannot take the log of 0. So all of our objects, after we've substituted our values in, have to be greater than 0. By getting the log by itself, so I've kind of highlighted here what the log by itself means, log base 9 of x plus 8. So we've got, it's both got a coefficient of 7, and it's got a number subtracted at the end. So we want to get rid of those first. So the first thing I'm going to do is I'm going to add the 2 to both sides. Getting rid of that 2. That's going to give us 7 log base 9 of x plus 8 now equal to 7. All right, so now I want to get rid of the coefficient. It's being multiplied by 7, so I'm going to divide both sides by 7. And it's going to give us log base 9 of x plus 8 equals 1. Our log is now by itself. Log base object, that's all we need. Right? So now we're ready to write it in exponent form. Right? So we know our base is 9, we know our exponent is 1, and it would be equal to our object x plus 8. Right? So when we write that out, let's see what that looks like. Right? So we have 9 to the first is equal to x plus 8. Right? So no more logs, we're ready to just solve for x. Right? Just regular algebra 1 equation, right? So it's being added by 8, so I just need to subtract both sides by 8 to get our final answer that x is equal to 1, right? So we solved, we've got x by itself. We just want to double check that if we were to take 1 and substitute that back in to our object, is this going to create an extraneous solution? So remember, we don't want 1, we don't want 0, and we don't want a negative value. So if I substitute in 1, that's going to give me a log of a positive 9. So that is good to go. So x is equal to 1. If it's not extraneous, we're done with that solution. Next example we're going to go over is solving equations with 2 logs. So now we're going to have a combination of logs or multiple logs in an equation. We're going to need to get them into 1 log and then solve. All right, so solving equations with 2 logs. I'm only going to do with you guys this example B, but I'll go through the steps first. I will have the worked out solution to example A, so you can always go back and look at it. in the printed and in the video as well. So first step, when we have two logs, the first step is to get them on the same side of the equal sign, okay? So here I've got logs on opposite sides. I need to subtract one of them or add one of them. I got to get them to the same side. Okay, then we're going to use our properties of logs to combine. So we're going to condense our logs so that we only have one log. And then we're going to exponentiate. Okay, and that's it. The rest of the problem is the same as the previous examples. We're going to change it to exponential form and then get x by itself when we're ready. So just say exponentiate and solve. All right, so let's look at example B. Okay, so this one's done. I'm not going to go over it with you, but you can look at it later if you want. I'm going to look at example B. So both of these logs are on the same side of the equal sign. I'm going to need to condense them. So I'm going to condense by first getting rid of this coefficient of 1/2. Remember, that's going to turn into the exponent over here. It's going to be the exponent of x, so x to the 1/2. Don't forget that x to the 1/2 power just translates to the square root of x. Right, so we'll see that simplified in a little bit. So I've got two logs, log base 2 of x to the 1/2 now, and log base 2 of 10. And we want to combine them since they're added. That means that we're going to need to multiply these objects together using our product property. All right, so I can put those together into one log, log base 2 of 10 times x to the 1/2. Right? So I'm going to write that as log base 2 of 10 times the square root of x. Now I've got the log by itself. There's no coefficient. I don't have anything added or subtracted at the end. I've got a base, an exponent, and an object. So we're ready to exponentiate. Let's turn it into exponential form. So I have base of 2 raised to the first power is equal to 10 square roots of x. All right, so now we're dealing with an equation where I want to get x by itself. It's being square rooted and it's got this coefficient. So I'm going to get rid of the 10 first. It's being multiplied by 10. So let's divide both sides by 10. All right, so when I divide both sides by 10, I'm going to get 2 over 10. All right, 2 over 10, which just simplifies to 1/5, 1 over 5. And then I've got the square root of x on this side. So I want to get rid of the square root. We get rid of the square root by squaring both sides. So we're going to square both sides. That's going to leave me now over here with just x. So really, once I square 1/5, I'm done. I found my answer. So x is equal to 1 over 25. All right, last example, I'm not going to walk you through this example because it's very similar to the last one, but this one is just an example of what happens when you have an extraneous solution. How do you know if it's extraneous? So in this example, we had to combine the logs. We condensed them to one, set it up in exponential form, and then once we get x by itself, x is equal, it actually has two solutions. It's equivalent to positive and -4. So I have to go back in and double check that if I were to put those numbers into my object, I don't have a negative or a 0. Well, if I take -4 and substitute it in for x, I'm now taking log base 2 of -4, which means I've got a problem. So that -4 is an extraneous solution. So that means that 4, it is working. It does work. So 4 is our only solution for this problem. Even though we found algebraically two solutions, -4 is extraneous. 4 is our only working solution.